Okay, Year 12. Our syllabus point here is about, we're moving over to instrumental quantitative analysis tests. Excuse me. So, we're finding out about metal and species in solution through instruments. We're going to group together colorimetry and UV visible spectrophotometry or spectroscopy. I'm going to do that later. I'm going to do first atomic absorption spectroscopy. Okay, so in general, instrumental quantitative techniques involve using an instrument to achieve or obtain a series of responses for different concentrations. And then what you do is you run your unknown sample through the same machine and compare its response to the known responses. Okay? So usually spectroscopy or spectrophotometry, we're using energy from the electromagnetic spectrum to cause some type of absorption or with absorption with the chemical species. Okay? So all of these we're looking at absorption. Okay? Absorption of certain light. So, as I was just saying, we'll talk about AAS first, or atomic absorption spectroscopy, and we'll group colorimetry and UV spectroscopy together because they're very similar. UV vis spectroscopy is also used for organic analysis, and so I said we'll cover it in the next chapter, but I'm pretty sure we've got it in this chapter too. Let's just run with it. Atomic absorption spectroscopy, sometimes abbreviated as AAS. Okay, so it is an instrument to determine the concentration of metal ions in solution. So it's good for metals only. Okay, it is extremely sensitive. This means it can detect low concentrations of analytes or metals in the order of parts per million range. And remember, parts per million in solution is equivalent to milligrams per litre. Okay? It's very useful when we're analysing toxic metals, which are dangerous at very low concentrations or trace levels. Okay? Because the other methods cannot detect them. So, because the limits of detection for chemometric for titration's example are too small. So, for example, if you use the titration that we're talking about earlier, Volhards, we get our precipitate. And that precipitate, the mass of it would be so tiny that it will stick to the filter paper and you'd never be able to remove it, and you put it on your 2 decimal places on your digital scales and there'd be no difference and it would be lost. But still, it being there can be quite toxic. Okay, so very sensitive, it can detect small concentrations. So very good for trace metals, trace things, and toxic things. So, commonly used for, well, it's commonly used for a lot of things, but what ends up coming up a lot in problems, concentration of lead in paint. Yeah, paint used to contain lead oxide as a white pigment. Concentration of lead in soil. Lead used to get in soil because lead was added to petroleum as a lubricant in engines. So it's a problem around old roadways. The amount of mercury in fish, so mercury getting into waterways from mining and stuff like that. And the amount of cadmium in mine water. So remember, we're talking about heavy metals in mine water at the beginning of this chapter. Okay, so lead paint contains tetraethyl lead from the fuel. Those type of problems come up all the time. Okay, from the textbook, here is a schematic of what's happening inside this atomic absorption spectrometer. Okay, and we're going to follow this through step by step and talk about each component. And here underneath, I've got an actual photograph of atomic absorption spectrometer. It has some casing that's been removed, so you can see inside it a bit. Okay, I'm sure I've got other pictures with the casing. Okay, so to analyze for one particular atom, so you analyze for one particular metal atom at a time, what ends up happening is you have a hollowed cathode ray lamp There's 4 of them in this machine, but they're all, well, not identical, but identical in form, but I'll talk about the differences in a second. So these lamps contain a sample of that metal that you're trying to analyze for. And electricity runs through this cathode ray lamp and it excites the metal filament in there. And that emits its spectrum, its signature spectral lines from electrons being excited. Okay, so it emits that spectrum out and we produce that in a little bulb, and we're going to direct that at our sample. Okay, for example, if we want to analyze for zinc, we'll use a hollow cathode lamp with a zinc filament in it. If we want to analyze for lead, we'll use a hollow cathode lamp with a lead filament. Okay, so when you look at the machine, most modern ones have multiples of these lamps that you can put in. This one here's got 4 that you can switch between without removing the lamp. But alongside each of those machines, there's a whole lot of boxes with lamps in them. You can buy lamps for all the metals, pretty much, I think. I've seen a lot of them. So they just come in boxes and you can switch these lamps in and out. They just attach in like a light globe, actually. So you can switch those 4 out. It's just that it has the capacity to have 4 in there, so you can quickly analyze between 4 at the same time. But you have lamps for each of these metals, okay? So any metal that you can analyze, companies that make these machines make these lamps ready for use, okay? So the lamp needs to be the same as what you're analyzing for, okay? So the hollow cathode lamp up here, electricity comes in, that analyte metal is there, and it produces and outputs one of these spectra that's going to follow this dotted path. So the light is pulsed as well, okay? The next thing in our diagram is the burner or the flame, okay? Our sample solution is going to be sucked up by vacuum, a little tube. So here's our sample that they're analyzing. A little tube sucks it up, puts it through a series of little things, and then spits it into this flame, okay? Sucked up into the instrument, sprayed as small droplets, or aerosols is the technical word, into a very hot flame, okay? Most of the time, this flame is a mixture of air and old name acetylene, new name ethine. It gives a flame of 3,100 degrees Celsius. So it atomizes everything. It breaks all the chemical bonds in whatever you're putting in it and makes your sample and what's coming through into individual atoms. It's that hot, okay? So it overcomes all bonds. Oh, look, that's just what it says here. So only individual atoms are traveling through that flame, okay? So as light's hitting that flame and our sample's going through that flame, so staying there. The spectrum of the analyte that was produced here at the hollow cathode ray that's going through the flame will hit your sample, and when the analyte is there, it's going to absorb some of that spectrum. It's going to absorb some of that light or take away some of that light. So these spectral lines are going to get dimmer, okay? If there's a lot of the analyte there, they're going to be very, very dim. If there's not very much, it's just going to dim a little bit. And so that's what I've tried to show here, where here's the light going in, and here eventually is our light coming out. You can see all I've done there is dimmed it, okay? So our sample's going to absorb some of that light, okay? And the amount of light that is absorbed is proportional to the concentration or the amount of stuff that's going through that flame, okay? So the intensity of the spectrum after the flame will be less. It's going to be dimmed before the flame. Some light is lost, okay? And that's proportional to the concentration. And remember, the electrons are going to absorb that and get excited out to an outer wavelength, okay? All right, so that's what's happening in the flame. So this side of the flame is this one. This side of the flame is this one here. Dim, 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 okay? Depending on how much analyte you've got going through. Okay, what happens here at our diffraction grating and monochromator? We've got a slit, so it only accepts a part of the light. So our spectrum, our reduced intensity, comes through this slit, and it hits this diffraction grating. And a diffraction grating is a surface that has very tiny ridges on it. So this one here with its big ridges is an exaggeration. It has tiny ridges, and what that does is just spread the spectrum out, okay, like a prism. Or another way you could do this, and if you actually pull apart one of these machines, it has the same pattern as an old CD disc, the back of it, where it splits apart the light. Okay, so it splits apart the light into all of its spectrum, and from there it sends it on to a curved mirror and then through another slit too. Okay, so the monochromator is a curved mirror. So this curved mirror, it just selects one of the wavelengths coming off this rainbow maker or this diffraction grating, and it shoots it through to the detector. Okay, one of those wavelengths. Okay, and we set that wavelength in the computer that runs this. Okay, it is usually the most intense wavelength that's given off for that. So here for this analyte, we might want to select this yellow line here or the orange line there, and we'll set it to just looking at how much that dims. Okay, at the end of that, we've got this output display or this measurer. Okay, what that usually is a computer. So what it does is just, well, a little bit more. It has a light detector, and the computer knows from the hollow cathode ramp how much light went into the sample. The light detector at the end knows how much came back out, and it does a calculation, and that calculation is called absorption. Okay, and it's a logarithmic relationship between the initial intensity of light and the final intensity of light, and it does a calculation. And usually for this instrument, we have a value below 1.00 or something, around below 1. Okay, the important thing here is that the absorption is proportional to the concentration. So in a y equals mx plus b plot here, our absorption or y value is some constant times the concentration and shifted up or down. Okay, so we're trying to find the relationship between absorption and concentration. So here's an older AAS. So the flame is in here, in this part here. I should draw that in orange, shouldn't I? The flame is in there, and it's sucking the sample up, and the fumes are going out there, and you've got a computer that's comparing the input light to the output light, doing the calculation. It's a very old computer too. Alright, so a couple of comprehension questions. The atomic absorption spectrophotometer was developed by Sir Alan Walsh and his team at CSIRO in the 1950s. Its development was one of the most significant in Australian chemical technology. What did it provide? A rapid method to monitor chemical pollutants in water supplies. Well, it can do that. The first method for determining the concentration of metal ions in water supplies. Well, no, we can do it chemometrically. A method for determining the concentration of hydrocarbons at very low concentrations. Well, no, it's for metals. A method for determining the concentration of metal ions at very low concentrations. This is the most correct one there. Okay, we're dealing with metals at very low concentrations. Okay, which of the following greatly enhanced scientific understanding of the effects of trace metals? Oh, improved filtration? The development of atomic absorption spectroscopy. New elements in particle accelerators? Nah. Le Chatelier? Nah. AAS. Okay, trace elements, trace metals. Okay. A section of the emission spectrum of a mercury lamp is shown. So we've got a cathode lamp with mercury on the end, and it's got emission lines coming out, or different colours. Here they've just shown two. Okay. Light at this one and this one from the mercury lamp was passed through a sample of water containing mercury, and the intensities were measured by the detector. So I at some nanometers, and then I, the detector, so the lamp and the detector, okay, the light. Which of the following pairs of intensities can be used in the determination of the amount of mercury in the water sample using atomic absorption spectroscopy? Remember how I said that the computer, you select one of the main wavelengths, okay? And you compare it going in to it coming out. You don't compare this one going in to this one coming out. You keep them the same. So the intensity, so you could either, for this one, select the intensity of the 623 wavelength going in and compare the 623 coming out, or you can select the 615 and compare the 615 going in to the 615 nanometers coming out. You can't mix and match the both, okay? And that's what this question is testing you about. Look at A, 615.2, 615.2. 615.2, 623. 615.2, 623, 615.2, 623. You've got to keep them the same. So we're comparing the light from the lamp at 615 to the light in the detector at 615. Okay, you've got to keep them the same. Alright, so once we've got these absorption values, what do we do? Okay, we need to determine the relationship between absorbance and concentration of that element. And we do that by constructing a calibration curve, okay? It's a graph of known concentrations and measured absorbances, okay? It looks like this. So first, we need a series of solutions that contain the same element as what we want to test for, and we want it in around 5 different yet known accurately concentrations, or we want 5 solutions with known concentrations, okay? And then we're going to measure these known concentrations, we're going to measure their absorbances. So here, for example, we've got a pink substance here, and we've got it at different concentrations that we've made knowingly. So 0, 1, 2, 5, 10, and 20 ppm. And what we're going to do is measure the absorbances of those. And then we're going to plot it on a graph of concentration versus, not peak area, that's terrible. We should have it as absorbance. Okay? And what we're going to see is a linear trend, and we're going to get a line of best fit there. Okay? And therefore, we're going to know the relationship between absorbance and concentration. From there, we're going to get our samples of unknown concentrations and run them through the atomic absorption spectrometer and measure their absorbance, okay? And then what we'll do is we'll use the graph to go, oh, this one had absorbance here, dot, 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 down. Its concentration must be that much, okay? So their absorbances should be within the range of calibration concentrations, okay? So it should be within there. If the absorbance is too high, if it's coming up here, what we do is dilute it so it is back in that range, okay? Oh, that's what I talk about here. So there's 2 common ways, but in an exam, you'll be doing it by drawing a graph and dot, dot, dotting, okay? You can form a y equals mx plus b in a spreadsheet and do your calculations a bit more precisely, but you won't be doing that in an exam, will you? Okay, so let's have a go. Here's a past paper question. A university student decided to measure the concentration of lead in the soil around his home. He prepared 5 standard lead solutions of known concentration, and 1, 2, 3, 4, 5, and the 0 and the absorbances of these were measured. Here they are in the table. These results are shown in the table. Now we need to do a line graph. Look, they've done our they've done our scale and all that. We just need to put our data points in there. Okay, so 0 was 0. That's good. 1 ppm was 0.15, which is about there. And then 2 ppm was 0.31, which is just above the 0.3. And 3 ppm was 0.44, which is right there. And 4 ppm was 0.59, so just under the 0.6. And 5 ppm was 0.75, which is just up here. Look how linear that is, okay? So from there you will draw a line of best fit. I don't have a ruler with me. Let's see how I go freehand. Oh, that's a bit wobbly. Oh, you know what I can do? Oh, look at that. All right, so you'll use a ruler and draw a line of best fit. Okay. So now you know your relationship between concentration of lead and absorbance through AAS. Okay, the student prepared solutions of 4 different soil samples around his home. These solutions were also analysed using the same method, and the results are shown. Okay, so we've got absorbances from all of these ones. Okay, determine the highest concentration of lead in the soil at home. Well, the highest concentration will be the highest absorbance. Okay, as the concentration goes up, absorbance goes up. So what is the highest absorbance? 0.11, 0.22, 0.22, the mailbox. So mailbox. And it equals the concentration. So the absorbance is 0.22. I'll change my colour. What should I go for? I'm going to go for pink again. Blue. So 0.22. We'll find it on our graph. So it intersects there. And then we'll come down. And it's pretty much on the 1.5. So the concentration of lead, 1.5 ppm, or that's also milligrams per litre, remember. Okay. State a hypothesis to account for the variation in lead concentration around the student's home. Okay. So the highest was at the mailbox. And the second highest was the front garden bed, which I'm assuming is near the mailbox. The back garden and the back fence had much lower. So concentration was highest at the front of the house and lowest at the back of the house. As I was saying earlier, petroleum used to have lead, tetraethyl lead, or a compound with lead in it, for lubrication. So it's at the front of the house because it's closer to the road where leaded fuel was used. Okay, so let me just write that. Since leaded fuel was used into the 1990s, the higher concentration of lead is likely due to being closer to the road. Okay. All right. Let's try another one. Okay. So they're quite identifiable, these questions, because you'll have your absorbance and concentration table and then a graph underneath it. And even in this one, they're still giving you the scales on the graph, but you can easily do it yourself. Okay, analysis of cadmium. Excuse me. So let's plot it out. So 0 was 0.0. 3 was 0.22. So about there. 6 was 0.38. So just under the 40. 9 was 0.62, so just after the 0.6, and 12 was 0.83. Oh, so about there. All right, do my line of best fit. That's pretty good. All right. Okay. Further along, the map shown is a catchment area. There is an industrial plant and a sewage treatment plant and a small town downriver, all of which discharge water into the river. Water samples were collected at 4 sites. Okay, 1, 2, 3, 4. Look at their different absorbances, and it's cadmium levels of the 4 sites. Justify your conclusion about the most likely source of the cadmium. Is it from the mountain range? I don't think people are pooping out cadmium. I don't think cadmium's leaching from the town or the mountain range. I think the industrial site is the source of cadmium. Okay. Actually, that's just using my knowledge here, but let's look. I didn't even look at the evidence. Okay, let's look at the actual information given to us. Okay, site 1 was low. Okay, so low. Site 2 was low as well. Oh, well, site 2 was a little bit higher. So 0.15. Site 3 was 0.55. So a big jump there. And site 4 was a bit diluted. So the highest was around site 3. So it was around the sewage treatment plant. So justify your conclusion about the most likely source of the cadmium pollution. Alright. Well, site 1 didn't introduce... Well, this is a bit... If they had one after the sewage treatment plant, it'd be good. It's still site 2, industrial site. Industrial plant. I'd say it's just accumulating at site 3. Terrible question. I'd put the sites a bit different. It's still from the industrial site. I mean, people aren't pooing out cadmium, are they? Actually, here's the theory for you. Cadmium's coming out, travelling downriver. People are drinking the water. The water's going, their urine is being treated, putting up there. It's not coming out of the treatment, and it's concentrating. Oh, I shouldn't laugh. That's probably what's happening. Everyone in the town has got cadmium poisoning and is urinating into the sewage, and it's going all the way through and concentrating up. Thanks for that question, past HSC. Okay. Atomic absorption spectroscopy worksheet. Also, here's some good videos. There's 2 videos of AAS, atomic absorption spectroscopy machines working. They're very important to get your head around a bit more what they're doing. Okay, it becomes a bit more clearer if you've used one, but under the circumstances, have a look at those 2 good videos. And here, here are 2 people working through calibration curves as well, helping you out there. Okay. All right. Have a look at those videos. They're very good. There's a example from the textbook too, and then we'll talk about colorimetry and UV vis next.